Hello, everybody. My name is Qing Yang. I'm a CS PhD student in University of Georgia. Today, I will introduce my paper, Needs-Driven Heterogeneous Multi-Robots Cooperation in Rescue Missions. So I will separate the 5 parts to introduce my paper. First is the introduction. So this paper is mainly focused on the urban search and rescue missions, USAR. The rescue mission can be regarded as a life-saving, delivering valuable properties, and tackling crucial facilities in disaster or emergency scenario, which involve the complex, hazardous, uncertain, unstructured, dynamic, changing, and adversary environments. So for the multi-robot system working in such a scenario requires to have a rapid response, higher adaptation, and strong robustness, which will largely help with minimize the loss in the post-disaster scenario. Research in robots as USAR aims to increase mission success rates, improve the execution efficiency, and minimize the system cost during the rescue mission. So currently, the most related works focus on the problem of the environment monitoring, structure, inspection, navigation and control, and high-level autonomy. Also, there are various advancements in rescue robotics through the development of the heterogeneous human-robot teaming methods in disaster response scenarios, disaster detection, disaster monitoring, target tracking, victims detection, and reinforcement learning-based semi-autonomous controller for urban searching and rescue missions. So for the problem part, we find considering grouping robots with various capabilities cooperating to pursue specific goals, less literature study the integration of the organizing agents' behaviors, solving the conflicts, optimizing system utility, and boosting system adaptability and robustness for the entire group. Also, there's little research done from the agent's needs perspective, studying individual interaction and behavior for system performance and global actions in MRS, especially in disaster robotics. So this paper just provide 3 kinds of contribution. First, we generalize the problem of the rescue mission through the use of the different groups of the robots, such as the carrier, supplier, and observer. And we formalize the multi-robot cooperation through robots needs hierarchy encoded in a behavior tree structure. As you can see, the left graph is just our model. Then we theoretically analyze the rescue robot teaming from 2 perspectives: utility achieved by the robots group and the energy consumed by the group. Lastly, we verified the theoretical results through simulation with different teams of the homogeneous and heterogeneous robots deployed to a rescue mission. The problem statement is mainly based on our preview work, the robots needs hierarchy. As you can see, for the 3 kinds of the robots, carrier, supplier, observer, we all all define a specific capability and distribute in corresponding level. So for the robot safety needs, each robot both have a communication, perception, and moving abilities to guarantee the safety issues. And the basic needs, which means the robots need have a basic energy. I mean, the battery, the oil, and the water, stuff like that to support their normal function. And for the capability needs, if the robots want to achieve this, the specific task, they have a certain capability to feed the rescue mission requirement. So we can regard the rescue program as an optimization program, which means in a limited time to fulfill rescue mission to maximum the group utility based on certain requirements. And in the rescue mission, we consider the group utility as the number of the lives, the victims, or the valuable property saved and rescued as much as possible in a limited time. And this is the formalization part of the program. And in our theoretical analyzing, we just, in order to simplify our model, we just consider one specific rescue mission and n identical obstacles distributed in an uncertainty disaster environment randomly, and use the very basic, statistical concept like the Poisson distribution and expectation calculation to verify our model. And for the detail, you can just look at the paper. Finally, we can just estimate the grouped expectation utility for each scenario and compare their performance. So for the evaluation part, we select the Unity game engine and build a simple scenario to verify our results. And for the experiment setting, we designed two kinds of the experiments: homogeneous and heterogeneous multi-robots cooperation, and consider two categories of the robots, carrier and observer. And as you can see, we have 4 kinds of the scenario. One is the 6 carrier, the second is the 6 observer, and the last 2 is the 3 carrier plus the 3 observer non-cooperation, and the 3 carrier plus the 3 observer cooperation. And I can play the simulation model for you. So for the first scenario, we just assume the carrier have enough, the basic needs. I mean, the energy to support them to fulfill the entire task. So as you can see, they do not need to recharge in the whole process. Yeah. So for the second scenario, the 6th observer, since we assume they have limited energy, so but the speed is much faster than the carrier, but they need to recharge to the recharge and back to work. And as you can see, they have a 3 round to recharge. So for the third scenario, we just consider 3 carrier and 3 observer to fulfill the rescue mission, but those 2 groups do not have any communication and cooperation with each other. They just fulfill the task separately. And as you can see, the performance do not improve pretty much. So for the last scenario, we consider the 3 carrier and 3 observer cooperate with each other. And as you can see, the performance is pretty good compared with the other 3 scenario. So through this experiment, we get some conclusion. First, the heterogeneous MRS creation not only delivers more excellent group utility and less system cost from the system perspective, but also saved more cost per rescue unit from the individual angle. More importantly, from statistical perspective, comparing with the rest of the scenario, the heterogeneous cooperation system decrease the performance the uncertainties and provides more stability and robustness for the whole system. It can help the system adapting more complex and uncertain environments efficiently and presents more robust viability. So through this paper, we represent an overview of a needs-driven cooperation model for heterogeneous multi-robot system. We advanced the robot's needs hierarchy established in our early work and formalized the general rescue mission and categorized the robots in USAR mission as a carrier, supplier, and observer. Last, we verified the homogeneous multi-robot cooperation increased group utility and robustness, and decreased energy cost and performance uncertainty compared to the homogeneous multi-robots grouping for the same task execution. So for the future work, we might mainly focus on the human-robot teaming. And we just list the 3 kind of the direction we want to pursue. One is adopting a suitable formation to perceive and survive environments predicting threats and explore new rescue tasks. Reasonable path planning adaptation in various scenarios, avoiding collision, guarantee human security, and decreasing the interference for human working environment. Last is comparing the specific capability and needs of the robots and humans, calculating a sensible strategy to organize the entire group collaboration, fulfilling corresponding rescue mission efficiently. Okay, that is our work, and thank you very much. I hope you guys enjoy our work. Okay.